All right, right on time. Okay, so coming back to this lecture. Okay, last time we actually look at, right, so how to represent the Boolean function, right? Oh, there's one more question. Right, so again, I guess you guys are still asking about quiz, right? So the quiz will be the next question, right? On item phone. I haven't started that one yet. Right, so let's look at let's try to review some of this concept again, right? Last time we looked at this function, right, in the proofs lecture. Okay, now we have this so-called A and B, right, not, right, which is we want this A and B, right, to not be equivalent with this B plus C naught, right? And this is the truth table that we laid out, right? And then we talk about this concept of canonical forms, right? Actually there's some question about, there's still some confusion about canonical sum and product, right? If you look at canonical sum, so we look at truth table and we focus on the onset, right? We look at the rows which have a 1, right, in the output column. And then for each one of these rows, right, so we have an input combination, right? We just need to translate this input combination into the corresponding normal product, right? Basically min term. All right, so this is the canonical sum, right? And there's this another shorthand, which is the summation, right? So we actually use the summation. So, and we just need to sum up the indices of these min terms. That's it. And we can also do a canonical product, right? In this case, actually the size of the onset, right, the same as the size of the offset, right? So for canonical product, we look at the zeros, right, in the output column, and we look at the corresponding input combinations again, corresponding rows again. And we call this is offset, right? And the main difference here is, so if we translate this each one of this row into the max term, right? Over here we have product max terms. So if we have a 0, right, in the input combination, right? So for max term, we use positive literal. Otherwise, if you 1, we use a negative literal. Okay. All right. So actually, this truth table is very much similar to the one that the extra set that we did, right, for the quiz last time. All right. And for this lecture, we're going to be talking about how to simplify, right, this kind of Boolean functions. Any more questions about canonical terms or normal terms, right? Canonical sum, canonical product, right? Once again, min term, right? Min term is a normal product. Max term is a normal sum. Okay. So let's look at some of this new concept, right? So first one is a very important concept. Okay, it's called combinational logic. So when we say combinational, we are looking at the Boolean function or looking at the logic where the output depends only on the current inputs. Okay? It's actually going to be more clear when we introduce something else called sequential logic. But in this lecture, everything is just combinational, right? Again, so for example, if we have a logic or Boolean function that try to detect whether input is an odd number or not, this is actually a combinational logic. And usually we can either use it, express it using a 2-level form or multi-level form. In this lecture, we're going to be talking about 2-level form. Next lecture, I'll briefly talk about multi-level form. It may not be too clear, right? So what exactly is combinational logic? So first, let me quickly define what's the opposite, right? The opposite to a combinational logic is so-called sequential logic. This is the kind of logic where we have memory inside or we have state inside. Okay, for example, if you have a circuit, digital circuit, right, which can detect whether the last 2 or previous 2 inputs are odd or not. That's where we have a so-called sequential logic. Right? I know you guys may still have questions, right? What do we mean by last 2, right? How do we determine the time and such, right? So these are topics that we're going to cover later on. But over here, see here, for sequential logic, we do have this notion of memory, right? Somehow, we can somehow memorize the last two inputs. If you can do that, then we have something called sequential. Otherwise, if you do not memorize anything, right, the output directly depends on the input, the current input. We have something called combinational. So far, everything that we have seen, right, AND gate, OR gate, NOR gate, those are all combinational. Okay. All right. And like I mentioned, right, so there are two different ways to represent the combinational logic. One popular way is using the so-called two-level logic form. And there are also two kind of two-level forms. So the first one is called the sum of product. In many cases, we will just use the shorthand, we just say SOP. Okay. For example, if you look at this one, right, this is actually a SOP, right? It's a sum of product terms. Is this one a canonical sum, guys? Yes or no? No, right? Good. Someone saying no, right? Because we are not using min terms here, right? It's not a canonical sum. And the reason this is called a two-level logic is it's going to be clear when you guys check out this circuit, right? So this is a corresponding circuit diagram, right? You see that we have three product terms, right? And each of one of them correspond to AND gate. So this is AND gate, right? This is AND gate, and this is AND gate, right? In case you're not familiar with the notation here, right? So what exactly is a bubble? So see here, we have a bubble on the input side. This bubble means inversion. Basically, we have NOR gate. We are inverting the input, right? So if you look at this one, right? This AND gate corresponds to this guy, right? A naught and B naught, right? So basically, the bubble means inversion. Similarly, right? So this guy means A naught, C naught. And of course, we need to OR them together, right? So this is where we have OR gate, three input OR gate. This is two-level logic because we call this AND gates, right? So this plane, this level, the first level. Okay. And then we have a second level where we do the OR. Make sense? Okay. So this is a two-level form. Right? SOP, right? Sum of product is one kind of a two-level logic. You guys probably can already guess, right? You can already quickly guess, right? There's another one where we inverse this, right? Where we have product of sum, right? Similar to where we do this canonical sum and canonical product, right? Same thing here. So we also have another form of two-level logic, which is called POS. Okay, so this is shorthand, right? POS, product of sum. Again, this is not a canonical product, right? This is since we are not using the max term here. Okay, similarly, very similar to the SOP, right, or sum of product. So over here, we can also represent it in a two-level circuit form. Right? Okay. But in this case, the first level is OR gate, right? The second level is AND gate. Okay. All right. Someone, Alma is asking, right? So if it's not canonical, right? So how exactly do we, right? How exactly does this formula come from? Right. Very good question. Right. So this is actually some of the things that we want to answer in this lecture, right? Like I mentioned in the previous slide, we in 2300, we usually follow this step, right? For two-level logic minimization, we first draw the truth table, and then we look at the canonical sum of product, and then we try to minimize it. Okay, we try to simplify it, right? So, and this is let's say, this example is the output of product from this simplification, right? Okay, and this represents the same function, right? In terms of functionality, there's another form, right, which is canonical, right? These two actually represent the same functionality. Okay, right. And in general, okay, this is a general statement. So any combinational logic can be expressed as either SOP or POS if you choose to use this two-level logic form. In the next lecture, we'll talk about multi-level logic. So we'll see, what's the advantage of multi-level logic, okay, versus two-level. Okay, we already briefly mentioned this, right? So once we get this canonical, right, sum or product, in many cases we do want to minimize it, right? We do want to simplify it. And we have already learned some tools, right, from last lecture. So we have learned these Boolean algebra theorems. Okay, we have learned quite a few theorems. But in this specific lecture, okay, actually for two-level logic, once we get the canonical form, so we'll mostly just use two theorems. Okay, you guys will see. Okay, only two theorems will be like useful. Okay, and they're good enough just to minimize the two-level logic. And we usually care for a few metric, right? So we usually want to minimize the number of terms, right? Minimize number of terms, and also per term, we want to minimize the number of literals. So these are directly related to the cost, right? So how expensive the eventual circuit is. Again, let's look at example. Okay, right? I'm going to answer some of the question again, right? So once we see the example, so we have seen this one before, right? So this is a 1 bit, right? So this is actually a so-called binary adder, right? So where we are taking 3 bits, right? A, B, C. So C over here on the input side called carry in, and output side we are producing 2 bits, right? One called sum, the other one is called carry out or C out. This is a truth table that you guys have seen in the first lecture, right? Just want to convince you again, this is indeed doing addition, right? Let's just focus on this last row. Okay, we are adding up 3 ones, right? So we are supposed to see a 3, right, as a decimal number. But on the opposite, since we are doing binary logic, right, binary circuit, so everything is in the in 0, 1. So if you look at the final output, right, there's a 2-bit output. So we indeed get 1, 1, which is a 3. Right? So we are doing addition here. You can also check out the rest of the rows. But one thing I want to quickly point out is, so over here we do have, right, so 2 separate output columns, right? So that's where, we actually need circuit, right? We need to derive circuit for both the S, the sum column, right? And also the carry out column, right? So 2 columns. And these are the corresponding, right? So these ones are the corresponding. This is the canonical sum, right? So we are using canonical sum here. So let's just first derive the canonical sum for these output columns. And let's say we just focus on the C out column. Okay. All right. Again, some of you are asking questions about this truth table, right? Now, what's intuition, right? So we will have a dedicated lecture on binary addition. Okay. So for now, just treat ABC as 3 input bits. Okay, so we are just adding up 3 binary digits. That's it. Okay, don't worry about other adders and such. Okay. All right, so let's focus on C out column and let's see how we simplify this, right? So we already have the canonical sum, right? Let's see how we can apply some of the Boolean algebra theorem to simplify this. Okay, so this is the expression, right? In fact, like I mentioned, right, so we actually only need 2 theorems. So one theorem is called combining. So do you guys see any opportunities here? So if you look at these terms, right, these product terms, you look at the last term, right, A, B, and A, and B, and C, A, B, C, right, and the first term, okay, A naught, B, C. Is there an opportunity? How many literals do we have in common? 2, right? Very good, right? Okay, so that means, and also if you look at the other one, right? So they're opposite to each other, right? A, right? One is A naught, the other one is A. So that means we should be able to combine them. Okay, just want to make it clear. Okay, you actually write it down. So we can do this, right? Which is just BC, right? Actually expand this out, but you can actually just use the combining theorem and to do it in one shot, right? Okay, and this is right one of the opportunities, right? If you marry this guy, right, with this guy, right, this two can be simplified. But how about this term and the second term? Do you also see some commonality here? Yes, right? Okay, so A and C, they're common. So we only differ, right, in B. So that means, this term, right, can also combine with this term, right, to simplify. But we only have one of them, right? We only have one of these terms. Can we use it twice? Right? So we do want this guy to be combined with the first term, right? We also want the last term to be combined with the second term. So ideally, we really want at least more than one of the last terms, right? So we can use it one more time. Yes, very good, right? So we really want to clone it, right? We want to clone the last term if possible. And indeed, we can do it, right? So by doing this, by using this theorem called idempotency, right? This the theorem is a fancy name. Right, so let's just clone it, right? First, and then after that, everything becomes very straightforward, right? Okay, we can use the blue term, right? And combine it with the first term, then we get B and C. And then we can use it, we can clone it again, right? Right, and then we use this blue term again and combine with the second term. Okay, we get A and C, right? So finally, we have three literal terms left. So again, we can combine them, right? So in this case, we'll get, right, just A and B. Right? This two. That's it. Make sense, right? So that's how we can simplify the canonical sum, right, into a simpler, right? This is SOP, right? Sum of product, right? I know many of you have already been looking at lab 1, right? So where we are using kernel map, right? Essentially, kernel map is just doing this, right? So while doing this, we're going to talk about kernel map, of course, right? So it's basically just a visual form. Like kernel map is a visual form of applying these two theorems over and over again: idempotency and combining. All right. Okay, so let's see, how much reduction that we get. So in this case, initially, right, if you look at the canonical sum, right? So we have, right, so these many logic gates, right? So we have 3 inverters, right? For 3 input NAND, 3 input AND, and 1 4 input OR, right? And after that, so we end up with simpler, right? So we end up with a simpler 2-level logic. So we only have a 2 input NAND. Right? Just want to convince you that I know there's some question about the cost, right? So since we are talking about this sort of abstract gates, right? AND gate, OR gate, we're going to be talking about cost, right? In the next lecture. So once we introduce CMOS, the cost of some of these gates will be more clear. But let's just look at 3 input AND, right? 3 input AND versus 2 input AND, right? So hopefully it's going to be clear to you guys, right? So which one is more expensive, right? Intuitively, 3 input should be more expensive than the 2 input one, right? Okay, because if you think about 3 input AND, right? Intuitively, you can actually implement it with two input AND gates, right? This is one argument, right? So just to convince you that indeed, right, 3 input one is more expensive, supposedly more expensive, right? Then at least not cheaper, right, than the 2 input one. Make sense? Okay. All right, so this is the simplification, right? Any questions so far? Right. I know, there are some questions in the chat window about, right, so when we write down the proofs, right, so what do we use? Will be clear. So when we give you the question, right, in the homework and exam, right? So whether we want you to write down step by step and then the name of each Boolean theorem or not, right, which theorem to use. So those will be clearly specified in the exam question or problem question. Okay,
yeah. I have a quick question. So just to clarify, so you first start by writing out a truth table, then you figure out the product of sums or sum of product. And then once you've calculated that, you then simplify and you've come up with a simplification of basically the equation that will give you your original truth table. Like that's the sort of flow, the workflow, right?
That's right, yeah. So what's your question, Jacob?
Oh, I was just clarifying on that
Right,
then.
right,
Yeah. So
right.
basically we do the sum of products or products of sum. We do the canonical sums and products just to make it so that we're in a position to simplify
Exactly.
later on. Okay.
Exactly.
Gotcha.
Right. But I want to stress again. So over here, we are focusing on two-level logic. Right. We're focusing on sum of product or product sum, SOP or POS. So that's where we start with the truth table and we write on the canonical sums, right? And then we try to simplify it. Again, in the end, we'll get SOP or POS. Okay. So let's talk about kernel map, right? This is something that some of you are already playing with, right? Essentially, like I mentioned, it's basically the application of combining and idempotency theorems, but in a visual way. And actually, kernel map is just a multi-dimensional truth table. So this is one to look at it. I'll give you guys the intuition behind a kernel map later, right? And the important thing about kernel map, so this is, make sure that you guys focus on this, right? To understand kernel map, the very important thing is to understand the intuition behind adjacency. So what exactly is an adjacency? What does adjacency mean in kernel map? Right? We already seen some of this, right? So when we look at this, CL column for this binary addition, right? So when two terms differ by just one literal, that's where we have the opportunity to combine, right? So this is what we mean by adjacent. So in kernel map, we have similar concept. We call adjacent cells. And also for kernel map, so for the kernel map we are going to be using, we will only use two variables per dimension. But I think some of these are still pretty dry, right, pretty abstract, so I'll make it very intuitive, very concrete one. Okay, so first let's define this kernel map, right? So for the function that we just saw. Again, let's focus on the CL column, right? So like I mentioned, the kernel map is basically a different way to represent the truth table, okay? So instead of using a 1D, right? So in this case, right? So the truth table is a 1D, right? One-dimensional column. But for kernel map, so let's say we use a 2D, right? So we use a 2D. This is, in this case, we are 2D truth table. And how do we fill in the things, right? We do need to define rows and columns, right? So the way that we do it in kernel map is, so let's say for rows, okay? So I'll use C, okay? This is C in, okay? For first row, we have C in equals 0, okay? For the second row, C in is 1. And we have, this is a 2x4 table, right? So this is a 2x4 matrix or 2x4 table. We are using C, right, to indicate right, to label the rows, two rows, and we're going to be using AB to label the 4 columns. Right? We have 4 combinations for AB, right? And the way to do it is, this is the label, right? So the first column is 0, 0, second column 0, 1, right? Which is very natural, right? But somehow, okay, for the third column, it's 1, 1, not 1, 0. And the last column is 1, 0. Okay, so this may seem pretty weird, right? But for now, okay, let's just memorize this sequence. And I'm going to reason about this, right? Why we have 1, 1, right, before 1, 0. Any questions about kernel map? So all we need to do is to, we just map this output column into this 2D table. So just to help you understand a bit, right? So you look at this one, this cell over here, right? This one corresponds to AB, right? So AB over here, AB is 1, 0. Okay, C is 1, right? So this really corresponds to the input row 1, 0, 1, which is here, right? 1, 0, 1, and see this column, output column. If you look at corresponding row, right, in this output column, we have a 1. Okay, all right. So let's see. There are some questions in the chat window. So is there Lawrence asking, is there an intuition behind why ones are compared with the canonical sum product? or should we just memorize that? Good question. Maybe let's look at the kernel map first, Lauren. So if you still have the, some confusion, right? So we'll come back to this question. And Rushi is asking, does it matter if you put two variables behind that line, like A above and BC in below? You're asking about the shape of the table, right, Rushi? For now, again, let's just memorize this shape, right, this sequence for now, okay? I'm gonna tell you how to construct your own kernel map, your own table, pretty soon. Okay, so this is basically the kernel map, right, for this CL column. And let's see how we use it. Okay, so coming back to this some of the definitions again, so kernel map. So first I want to define the so-called one cell. We will look at this table, right? So each one of these entries, right, is labeled with either 0 or 1, right, based on what we have in the truth table. So if we have 1 in the cell, we call it one cell. So for this actually corresponds to the mean term, right? Each one cell corresponds to the mean term in the canonical sum. And we have something called implicant. Okay, this is a mouthful, right? This is a interesting and important definition. So it's basically a set of adjacent. Okay, again, the notion of adjacency is coming up, right? A set of adjacent one cells, and it's a rectangle in the kernel map. So we need to highlight this, right? It's a rectangle, and the number of cells in this rectangle must be a power of 2. Okay? Must be 1, 2, 4, 8. Okay, right. So these are the numbers that we can have, right, in the rectangle for a kernel map. This is so-called implicant, right? So maybe let me just quickly check these guys, right? So is this an implicant? Yes or no? No, right? Because this one does not just cover one cell. So we only want to cover one cells, right? Is this one the implicant? Yes, right? So this is a rectangle. It has 2, right? 2 elements or 2 cells, and both of them are 1. Okay, so this is a implicant. And then we have something called prime implicant. Okay, just like prime number. Okay, we have something called prime implicant. So this is the kind of implicant that cannot be contained in a larger implicant, right? Again, this may look somewhat confusing initially, right? We'll make it very concrete very soon. Okay, but in this specific case, right? Let me just clear the sec. Okay, in this specific case, let me ask you. So is this an implicant? Yes or no? Answer is yes. Okay, this is a bit of a trivial case, right? So 1 is still a power of 2, right? It's still a rectangle. But is this a prime implicant? No, right? Because this implicant can be covered by this prime implicant, right? Make sense? Okay. So the larger one is actually prime implicant. In fact, in this specific example, you cannot find a larger implicant, right? You cannot find a larger circle to cover, right? So what we just draw over here, right? Okay, so one more time, right? So we have something called one cell, right? This is just mean term. Implicant is basically a rectangle of 1 cells, must be power of 2. And we're going to be defining adjacency very soon. And we have something called prime implicant. Okay, so which is basically something that cannot be contained in anything larger, in a larger circle. All right, clear? Okay, yes. So minus asking, right, can this one, right, go up and down? Yes, right. This is also prime implicant. This is also rectangle. All right, we'll see even weirder shape pretty soon. All right. Right, so this one is actually let me clear this again. So this one is actually a prime implicant. Right, this green one, a green oval or green circle. Yes, no diagonals. Okay. They have big adjacent. Okay, so once we have a kernel map, let's see how we use it, right? So the goal is to cover all the one cells with the smallest number of circles or minimum number of prime implicants. So that's the goal. So here's the steps, right? Here's the steps. So usually we first, right, plot, right? So we first plot a kernel map, right? We fill in the 0 and 1s. If you want to focus on this canonical sum, right? SOP minimization. So we want to focus on the one cells first. And we try to circle the largest rectangle, okay, the largest one, right? And again, it must be power 2, and it may include something like this shape, right? We'll see what exactly does it mean, right? Wraparound set. Okay, this is what I just mentioned, right? Something weird. Okay, you'll see. So we can include wraparound set as well, not just regular rectangles. And we'll keep doing this. Okay, we circle the largest one, and then we'll keep finding the one cells that are not covered, and then we circle them again until we are done, until we cover everything, and then we order them together. Okay. All right. So actually, if you just do this, right, so we end up actually minimizing the number of gates and the gate inputs in the SOP form. Okay. Right. There are actually some very good questions, right, on the chat window. Do we focus on the largest one or fewer circles? Actually, if you go after the largest one, if you follow this procedure, you will end up with the fewest circles. Okay. Although we are not going to try to prove it here. Okay, so let's see how we use it, right? This is the equation, right? There's an expression that we want to minimize, right? So at the bottom, we are seeing the corresponding kernel map, right? Okay, what we talk about, if you look at some of the things that we just did, right? We use idempotency to clone, and then we do combine, right? We combine the last term with the first term. So where exactly is the last term and the first term in the kernel map? It's actually here. Okay, just convince yourself, right? So this is indeed the case, right? Let's see, B, let's find, let's just try to find this guy, okay? A, B, C in. So A, B, C, and they're all positive literals, right? So we try to find A, B, is here, right? In this column, and C is here, right? The corresponding one cell is here. Since this guy is basically A, B, C in. Okay, and the other one is actually here, right? So A naught BC is over here, and we combine them. By combining them, we literally just have to draw a circle. That's it. Okay, we draw a circle that indicates combining, and we can continue some of the rest of the right. So combining, right? Again, we can clone this, and then we circle two other terms or two other one cells. So, right, so this is another combining, and we end up in the end circling one more, right? So I just want to clear this up. Okay. All right. Is it clear? Right. So this is exactly what we're doing. So it's combining. So basically circling this one cells, right? So basically each circle indicates the combining. So how about idempotency? I just mentioned, right? So we are doing both idempotency and combining. So where's idempotency? Where is it reflected? Yes, very good, right? The overlap, right? So see here, so this cell, right? This guy, so it's covered by 3 circles, right? So that means this guy is actually cloned twice. Make sense? Okay, so that's where we are using idempotency, and also it's okay that for us to form large circles, it's fine to cover one cell, one of the cells more than once. That's fine. Okay, as long as it helps us cover other cells, other one cells in a larger circle. That's one. Okay. This is basically the key things, right, about kernel map, right? We are basically doing these two theorems. All right. One more example. Oh, actually, let me go back. So just want to help you understand how to later on parse, right? So the output. So you look at the let's look at the blue circle, right? So if we circle two, we have a 3 input function, right? If we end up with a 2-cell circle, we circle 2 cells. How many literals do we knock out from this term? 1, right? We combine the ones. Of course, we knock out 1, right? Then we can just read it out, right? So if you look at this blue circle, how do we read out the corresponding product term? How to do that? So we actually focus on the common literals, right? So you look at this 2 1 cells in the blue circle, okay? So they're common in Cin, right? So that's why we write on Cin. And what else they're common in? They're common in A, right? If you look at these 2 columns, right? Both columns have A being 1. So that's where this blue circle basically correspond to A times or A and Cin. Make sense? Okay, so that's how we read it. All right, so if this is clear, let me show you something slightly more interesting. Okay. Again, we have a 3 input function, right? So over here we have 4 1 cells, right? So later on, here's the notation, right? Here's the convention. If you only want you guys to focus on 1 cells, right? So if the rest of cells are empty, that means those are just zeros. Okay, those are zeros. Okay, so what do we combine? We combine the whole thing, right? So this is a 4-cell rectangle, right? This is a prime implicant. Of course, this is the largest one, right? Now that we are combining 4 of these, how many literals do we knock out? 2, right? We combine 1, we combine 2, we knock out 1 literal. If we combine 4 of them, we can knock out 2 literals. So hopefully now you see the intuition why we actually want to form larger circles, right? Because we want to knock out more literals, right? So then our expression becomes simpler. So can you guys read it out? What is the corresponding term? What is the corresponding product term? Right, just A, right? Again, check out the things that are common, right? So what's common? Okay, since we are spanning 2 rows, right? So C is not common, right? We're spanning, this whole circle is spanning 2 rows. So C is not common. And the only common thing is A, right? This is a common thing. And in both columns, A is 1, right? So that's why we just write on A, that's it. Okay. Any other questions about this? If not, let's look at something a lot more interesting. Okay. So here's another example, right? Now we have 6 ones, right? So the way that we do things, do combining is we try to find the prime, right? Try to find the largest circle. Okay, so how many 1 cells do we have in the largest circle? What's your guess? 2 or 4, right? Okay, so most of you are guessing these 2 numbers, right? Of course, there's 2, right? It's pretty obvious, right? So we have opportunity to circle, right? So 2 of the cells. But some people are saying 4, right? Actually, that's a correct answer. Why is that? Okay, first, we can circle 2 cells, right? Over here. Then we can also, right? So this is, I'm not gonna read it for you, right? It's A naught, C naught. And we can also circle this guy, right? Okay, which is A and C. But the interesting thing about kernel map is actually we can also circle these 4 together, right? So somehow, the column on the far left is adjacent to the column on the far right. okay? And this is also a rectangular. Of course, this is not really the rectangular shape, right? In the traditional sense, but I'm trying to convince you that this is also adjacent, right? This is also rectangular. All right, so I'll give you a much more intuitive answer pretty soon, but if you just focus on this cell, right? And this cell, this cell and this cell, okay? Just compare the literals they have, right? And see how many literals is different. How many differ? Just one, right? So they differ in which variable? Again, we're looking at this cell, right? And this cell, but this cell is 1, 0, 0, and this cell is 0, 0, 0, right? They only differ by 1. That's why they're adjacent, okay? And they differ in A, right? They're common in BC. You can actually do the same for other cells, right? In the blue rectangle, but right, so they are indeed adjacent. Okay. All right, but this is still kind of weird, right? So so how exactly does kernel map, right? So why do we, how come this works, right? How come, we have this kind of adjacency? I'm gonna explain it pretty quickly. But any questions about kernel map so far? So we will do a quiz in a few minutes after I explain the intuition. So make sure you guys ask. Mamoon is asking, can we draw the map with, right, so I'm gonna explain that. Good question, Mamoon. Okay, so there are actually different ways of drawing kernel map, but in our class, let's just, right, so stick to this one in your homework and exam, but I'm gonna explain, right? So why this kind of arrangement makes sense. All right, so if there are no more questions, okay, so, we can, so this is basically B prime, right? So, when we combine 4 things, we knock out 2 terms, right? We end up with 1 literal. We knock out 2 literals. And we can just order them together, right? So this is the final form. All right. So, so far we have been looking at different kind of kernel maps, right? Different kind of adjacency, different kind of circles, right? Many of you must have this question in mind, right? So why do we use that specific sequence? Okay. So let me offer, my intuition. This is actually not something discussed in the textbook. I don't believe that it's discussed in probably other lectures. Okay, so basically, this is a special edition for you guys. Okay, so only accessible, available to you guys. Right. So think about the one of the questions I asked, right, in the first lecture, right? I asked you guys to look around and identify some of the things that you guys can encode using binary value, right? So, most of you are just, right? I think most of the answers are related to this so-called state, right? So, you guys mentioned whether the light is on or off, right? Whether the door is open or closed, right? Whether the tower is clean or dirty and such. I remember, so most of them are related to this so-called state, right? So we can use 0, 1 to encode the state of certain thing. But we can also actually use it to encode spatial information. Okay, what do I mean by this? Okay, let's say, most of you guys, maybe staying in an apartment, right now, maybe, right? You can use 0, 1 to indicate whether you are in bedroom or living room, right? So basically, this is my map, right? Okay, so this is 0 means I'm in bedroom, right? 1 means I'm in living room, right? Okay, so then if I use this spatial encoding, I can easily use it to encode the 0, 1, right? So then it's pretty straightforward, right? To encode 2 bits, right? If I draw, a space like this, right? Okay, I can just divide it into 4 cells, right? Okay, so I can, let's say for the rows, let's have 2 variables, A and B. Right? I'm saying for the first row, B is 0, second row, B is 1, and for the first column, A is 0, for the second column, A is 1. Make sense, right? I can just divide up this space into 4 cells, okay? And then I can encode a 2-bit variable, right? A 2-bit, information, A and B. How about 3 bits? How about 3 inputs? A, B, C. Okay, just keep dividing, right? Let's divide it into A cells, right? Now that we have 3 variables, right? 3 inputs. Let's say in the rows, C is 0, right? Second row, C is 1. And we also have A, B, right? What do we do with A and B? So let's say for the first 2 columns, A is 0. For the second 2 columns, right? A is 1. Right, so far it's pretty straightforward, right? But what about B? Can we do this? Can we say, again, for the first 2 rows, for the first 2 columns, B 0, and the rest B is 1? No, right? Because this means that these are not really 2 variables, right? A and B, they're always the same. Okay, when A is 0, B is 0. When A is 1, B is 1. What's the fix? Can we do something like this? Can we invert this? Still doesn't work, right? This means that B is always an inversion of A. Okay. All right, so then there's this challenge, right? Let me clear this. So I hope it's already, so the answer is already coming to your mind, right? So how do we encode this? Let me find my pen again. So the way to encode this is we'll use this area, right, to indicate B is 1, right? And we'll say for these 2 columns, B is 0. This seems like a valid encoding, right? Agree? Make sense, guys? Right? What is this? What is this? Right? So we can just read it off, right? What is this? We just say like AB, right? Indicates the columns, right? So we read this, right? So first column 0, 0, second column 0, 1, third column 1, 1, right? Last one 1, 0, equal to 0, 1. So here we go, right? So Carnot map is not magic, right? It's basically we basically use spatial encoding. We just divide up an area into multiple cells, and we just choose how we encode this binary information. As simple as this. All right. And someone will be asking, right? Is this the only way to do this? Of course, no, right? I hope you guys can come up with your own variation of Carnot map, right? So for example, we can just change it to be 0, right? And this is 1, and this is 1, right? This is another valid form, right? Okay, so this is the intuition behind Carnot map. But one more time, in this lecture and also in the rest of this class, we're going to be using this form, right? So we're going to be using the specific form of Carnot map, right? So where we go with this sequence, 0, 0, 0, 1, 1, 1, 1, 0. All right, so any more questions about Carnot map before I quiz you?